In this question, two masses are given, capital M and small m, connected by a rod of negligible mass. They rotate around a vertical axis. So this vertical axis is the axis of rotation. The ratio distance between capital M and the axis upon distance between small m and the axis is 1 upon 2. And we are supposed to find the moment of inertia. So let us start with the basic formula for moment of inertia, which is m1 r1 square plus m2 r2 square. Now let us consider m1 to be capital M and m2 to be small m. So r1 will be the distance of capital M from the axis of rotation. So let me label that. So capital M to the axis of rotation, let's say this is r1, and r2 will be the distance of m2 from the axis of rotation. The ratio of these two r's is given to us in the question as 1 upon 2. So we can write r1 divided by r2 is equal to 1 by 2. So let's write down r1 upon r2 is equal to 1 upon 2. Also r1 plus r2. The sum of two r's is actually equal to the length L, which is given in the question. So r1 plus r2 will be equal to L. So we have two equations here. R1 upon r2 is 1 upon 2 and r1 plus r2 is equal to L. Let us solve these two equations. If we cross multiply this equation, we will get 2 times r1 is equal to r2. Now let us put r2 in this equation. So r1 plus 2 times r1 will be equal to L. So let's write down r1 plus 2 times r1 equals to L. 3 times r1 will be equal to L. This means the value of r1 will be equal to L upon 3. And now since r2 is double r1, so let's write down the value of r2 will be equal to 2L upon 3. Now let us put the values in this expression. M1 is capital M, R1 is L upon 3. So let's write down capital M multiplied by L upon 3 whole squared plus M2 is small m, and R2 we just figured out was 2L by 3, and this will be squared. And let's solve this. We'll get M L square upon 9 plus small m into 4L square upon 9. And now let us take L square as common from these expressions. We will get m upon capital 9 plus small m into 4 upon 9. This will come in the bracket. And this is the moment of inertia of this entire system. Now, if you look at all the options, this expression is there in option B. So L square m plus 4m is in the numerator and 9 is in the denominator. So basically, we have just taken the LCM. 9 is the LCM and capital M plus 4m is in the numerator. And that is why option B is the right answer to this question. Moving on, now let us discuss some common shapes and their moment of inertia. So we have just discussed what was moment of inertia. It is a measure of rotational inertia. If an object has a large moment of inertia, then it is difficult for the object to rotate. And now let me show you two figures. Have a look. We have a ring with axis of rotation as shown. So the ring is rotating about this axis, and then another object which is the disk. Disk is also having the similar axis of rotation. It is passing through the center. Ring is a hollow object and disk is a solid object. Now please try to think, if we have a ring and a disk of the same mass and also the same radius, then which of the two, ring or disk, will be difficult to rotate? Is it the ring or is it the disk? So try to use real world practical knowledge. If you have a ring and a disk of the exactly the same mass, exactly the same radius, which of the two objects will be difficult to rotate? Now let me show you a video where we will see this in action. So look at this, the title of the video, race between a ring and a disk. So over here you can see we have a ring which is silver colored, and behind the ring you can see there is a disk. That brown colored object, that is the disk. Now understand the apparatus. There is an inclined plane which we have made, and we have taken a ring and a disk at the same point. The question is, if the ring and the disk are released at exactly the same time, then which of the two, ring or the disk, is going to come to the ground first? Will the disk reach first or will the ring reach first? Now remember, the rotation has a direct connection with moment of inertia. So whoever reaches late means it has a higher rotational inertia, which would mean a greater moment of inertia. So let me play this video and let's watch. When the race starts, did you see it? So the disk is actually traveling a lot faster than the ring. Let me play this video again. As you can see, the disk reaches the ground much earlier as compared to the ring. And here also you can see that the disk is moving much faster than the ring, and hence it reaches the ground first. So what we have observed in this experiment is the ring is taking more time to travel down the incline. Now the deduction from this observation is the rotational inertia of the ring is greater than the rotational inertia of the disk. So this is the deduction from the observation of the experiment. Now let us understand what is the reason behind it. So the reason is, further away the mass from axis of rotation, more is the moment of inertia. Now if you recall, we had the ring and the disk having the same mass. But in case of ring, the entire mass is on the circumference of the ring, which means every single particle in the ring is farthest away from the center. But in case of a disk, some particles are, of course, around the circumference, but a lot of particles are inside the disk also. And for the inside points, the R value, the radius value, will be smaller than the actual radius of the disk. Now, what do I mean by that? Now, let me explain. Let us label some points. Let me label point A, point B, and point C. Just for the sake of explanation, imagine the ring has only three particles, A, B, and C. Now, the distance of each of these particles from the center is equal, and that is equal to the radius of the ring. Now, similarly, let us label 3 points in the disk. So, we are assuming there are only three particles in the ring as well as the disk. So, for the disk, let's say one point is at the circumference, which is point A. Let's say point B is over here, and then we have a point C over here. For the point A, which is on the circumference, distance of the point A from the center is equal to the radius of the disk, but distance of the point B from the center is much lesser than the radius. Similarly, distance of the point C from the center is much lesser than the radius. And if you recall the basic formula, moment of inertia is m1 r1 square plus m2 r2 square plus m3 r3 squared. For a ring, r1, r2, r3 are all equal, and they are equal to the radius of the ring. But for the disk, only r1 is capital R, r2 and r3 will be much lesser than the radius of the ring. And that is why, remember the basic concept, moment of inertia is mr square. It not only depends on mass, but also the r. And that is why if the mass is further away from the axis of rotation, that object is going to have a greater moment of inertia. And since the greater the moment of inertia, it will be more difficult for the object to rotate. And in this case, rotational inertia of the ring, since it is greater than the disk, that is why the moment of inertia for the ring will be greater than the moment of inertia for the disk. So this was the complete analysis of moment of inertia. But in the exam questions, you should know the formula for a ring moment of inertia and moment of inertia for a disk. So just remember the formula. Moment of inertia for a ring is mr square, where capital M stands for the mass of the entire ring and r is the radius of the ring. Similarly, for the disk, moment of inertia is slightly different. It is actually half. So moment of inertia is mr square by 2. Hence, we can deduce that moment of inertia for disk is actually half the moment of inertia for the ring. Since disk is having a smaller moment of inertia, it is having least resistance to rotation. It can rotate faster, and that is why the disk reaches the ground first. So basically, the disk is winning the race between ring and disk. Now, apart from ring and disk, there are other shapes which we have to consider in this particular chapter of rotational mechanics. So the next object is a cylinder. So it's a hollow cylinder having mass m and radius r. Moment of inertia for a hollow cylinder is equal to the moment of inertia for the ring, which means moment of inertia is mr square for a hollow cylinder. Similarly, if we consider a solid cylinder, mass m and radius r, moment of inertia of a solid cylinder is equal to moment of inertia for a disk, which is equal to mr square by 2. So this was the case of cylinders. Now we consider a sphere, a ball. If the ball is hollow, so if the sphere is hollow, moment of inertia is 2 by 3 mr square. And if we have a solid sphere, then moment of inertia is 2 by 5 mr square.